Okay, so now let's have a look at the chaotic behavior of a continuous dynamical system, and we will look at a particular example. We will simulate Lorenz equations. The Lorenz equations are a very famous dynamical system where people identified chaos. It's one of the earliest examples, and it was proposed by Lorenz as a simple model of a weather system. If you simulate these equations for, let's say, for these values of S, R, and B, then you end up in a chaotic state. It's a chaotic attractor. So your system falls into this stable but unpredictable trajectory. And this is actually a real effect. It's not some weird artifact of numerical simulations. So you can in fact construct such systems in real from real physical components that exhibit this sort of dynamics. So just to prove that, I'll show you a video on YouTube which simulates a different. Essentially, it's a video which is looking at analyzes a particular circuit using an oscilloscope, and the circuit is called Chua circuit, and it exhibits also a strange chaotic attractor. It's different from the Lorenz attractor, but nevertheless it's a chaotic attractor. So let's have a look at what we see here. This is a limit cycle. This is a stable periodic solution. So what happens here, that there is a sweep of some parameter. At some certain values of these parameters, we will see bifurcations. Now here we just had a bifurcation, so now this is a periodic doubling. It was a periodic doubling bifurcation because now your period is twice. It doubled. So you see the two lines here. And remember, we had in our discrete dynamical systems, we noticed that we have a cascade of period doubling bifurcation before chaotic behavior. So let's see if we have some similar in this case as well. Here now we had a second period doubling bifurcation. Now this looks already like chaotic behavior. Your system does not really spend time in any particular places. Chaos then turns again into a limit cycle. Again some chaos. Yes, here. And now we reached, I think, a strange chaotic attractor, which actually visually does not look very different to the one we see here. Well, they are different, but it has some similarities, and this is actually a real physical circuit. So just to so that you appreciate that this is actually a real effect that can happen in real life. So now I want to simulate this Lorenz system, but before I do, I want to mention take a little detour diversion, so digression, right? And talk about something called delayed coordinate embedding, because this is something we may need in other courses, like self-organized criticality. So I'd like to mention that. So if you want to construct this kind of phase space diagram, you of course need all of the the time series of all degrees of freedom. So x, y, and z. And if it's more than dimensions, then you need additional variables. But that should be t here. But suppose you only have x of t. Suppose you only have the time series for one of the dynamical variables, and you don't know anything else. You don't even know the dimensionality of the dynamical system. Is it actually, so the question is it possible to reconstruct the phase space? Or if it was possible, then that would tell you something about the underlying dynamics, underlying mechanisms that generate the time series. And it turns out that it is possible, in a sense, to obtain the phase space diagram, but not exactly equivalent one, but topologically equivalent. So you can reconstruct a phase space diagram which is identical under some deformations, which is still good, because then by looking at the structure of the attractor, you can it basically tells you something about the system. So you do that using delayed coordinate embedding. So let's look at how to do this. So you have some signal x of t, or more precisely, you have a discrete time series. So you sample the continuous time series. You have a string of numbers, and then you embed it as follows. So you plot your phase space like this. So you have your time series, and then you shift your it's the same time series but evaluated at t plus some delay tau, and then on this axis you can plot t plus 2 tau. So you embedded your one-dimensional data into a three-dimensional space. In fact, you can go to more dimensions. You can you can go to 4, 5, and 6 dimensions. So that's going to be your embedding dimensions. But here, for simplicity, I represent it as 3 dimensions. And then then you use this Taken's theorem. So the Taken's theorem says that for the right tau and enough dimensions, the dynamics in this reconstruction space are diffeomorphic to the original state space dynamics. So diffeomorphic means identical and continuous deformations. So yeah, as I said, the given time series data, this kind of reconstructions gives us information about the dynamics that generated the data. So if you have some data from real world data, and it may look random to you, but if you apply this embedding, you may surprisingly notice that it could have some structure. So if you did the embedding and you end up with something which looks like this, which looks like some kind of chaotic attractor, then maybe the process is not random but is actually chaotic. So that's a basic idea, and one can develop it into a sophisticated tool for data analysis. So let's look at the example of the Lorenz equations simulated, and then just for practice, let's do this takens embedding and see if we can actually reconstruct the Lorenz attractor. Okay, so I prepared the Mathematica notebook for this. So we just do this the same. Try to reconstruct the first. Let's simulate the Lorenz system with the these values of S, R, and B. So here I define the equations, and yeah, let's simulate between t equals to 0 and t equals big T. So I set the final t to 30 seconds, 30 whatever units. Okay, this is my time series, which looks chaotic, irregular, and then I can also do a parametric plot of. So this is my phase space in 3D. Mathematica, come on. Mathematica is being slow. How do I get rid of this? Okay, I got this weird thing here. How do I get rid of this? Okay, but yeah, just have to do with this. Okay, so this is my 3D. You can see it's a strange attractor, and I can do also projections. So if I do projections, I get this. By the way, this projection looks like butterfly wings, and it's also one of the reasons for this phrase, a butterfly effect. Right? As an exercise, you can try obtaining the equilibrium points of the Lorenz equation as a function of R, well, given S 10 and B equals to 3. And then you can do the bifurcation analysis on each equilibrium points, find the critical thresholds. So this system does not exhibit chaos all the time, so it does exhibit also stable. For certain parameter values, it is actually stable spirals. And for an exercise, you can do this analysis, which is going to be very similar to this the worked example on the Fitzhugh-Nagamore model, the way we had hoped bifurcation. So you do find the equilibrium points numerically, do find the Jacobian, the eigenvalues of the Jacobian, and so on. So if you like, you can do that. It's not any very straightforward exercise. Yeah, but it's not that difficult either. But I'd like to look more into, rather than doing that, let's look at the takens embedding, because I think that's quite interesting. So let's do the delayed coordinate embedding as I just described in my lecture slides. So first, let's sample. We will evaluate x at discrete time points. So this is gonna be my discrete time series, right? So now, and then I do the delayed coordinate embedding with, let's choose the tau equal to 1. Well, 1 times 0.01. But essentially, I generate triplets from my values of x. So x, j, xj plus delta, xj plus 2 delta. And then I plot this in 3D plot. So this is what I get. Now suppose, let's see what happens when I vary delta. You see, as I increase it, you slowly start seeing the beginning of my strange attractor, Lorenz attractor. In a way, I'm zooming in onto this structure. So if you look at delta is to 10, I already have something which looks like Lorenz attractor, and I reconstructed this using just x. So this is the taken theorem says that this could be deformed into this topologically equivalent. And this is a simplified, of course. I'm simplifying this because in practice you have to. You don't know that you have to embed using. Maybe 3 dimensions is not enough. Sometimes you have to go to embed in 4, 5, and so on. But this is, and also there is a way of finding optimal delta to optimal for visualization purposes, which gives you the most amount of information about the structure of the attractor. But this is beyond our introductory course, and maybe we'll look at this in more detail in more advanced courses. Okay, so I will finish on this point. So let's summarize the lecture. We started with bifurcation analysis, so looking at how the stability changes as you vary some parameter in your system. Then we had a brief introduction into the chaotic systems. Particularly look at bifurcation diagrams and calculation of Lyapunov exponents for discrete dynamical systems. And then we had a very brief look at the continuous dynamical systems, and finally Taken's embedding. So this, don't worry if you found this lecture too difficult. You probably not going to use this material for your agent-based modeling assignment, but it's important to have an exposure to dynamical systems, so that you actually know what's more kind of formal, that there are more formal ways to look at this kind of dynamical problems. And yeah, if you do this equation-based style modeling, then it's important to know these techniques, how to find the stability points, equilibrium points, and their stabilities, and so on. But so if you do in the future, if you do want to look into more depths, then this textbook is very good. And I'm gonna try to. So for instance, there are many textbooks, but this one is quite nice. Nonlinear Dynamics and Chaos by Steven Strogatz. It's very accessible, and it's looking at in much more. It gives you much more examples and a systematic way of looking at nonlinear dynamical system that we could have done in the 2 lectures that we have. So if you want more examples, check out this book. Also, of course, read the Hirokisayama, the 2 chapters, chapters 8 and 9, and in general part 2 for equation style modeling. That basically completes our introduction to dynamical systems. And in the next part of our course, we will look go back to agent-based agent-based modeling, but look at some theoretical foundations for instance, deriving interactions between agents. So that's game theory. Okay.